Now let's move on to convolutional neural networks, which is very popular for images. We have studied linear regression and logistic regression models, and they both use linear layers, which are fully connected layers. If we use such layers for images, for example, if we have a 200 by 200 image, and suppose our first hidden layer is 500 units, then how many ways are there from the input image to the first hidden layer of a fully connected layer? So now you can pause the video and compute. So the answer is 20 million. So we need 20 million ways, which is 200 by 200 times 500. So this will become problematic for images. First of all, computing the predictions in a forward pass will take a long time because we have lots of parameters, lots of ways to be multiplied. And secondly, a large number of ways will require a lot of training data. This is to avoid overfitting. And thirdly, even a small shift in the image will result in a large change in the prediction. And lastly, this is not making use of the image geometry. Therefore, convolutional neural networks becomes very popular for images. There are two key ideas. The first one is to use locally connected layers. Such locally connected layers will look for local features in small regions of the image. Therefore, for each hidden unit, instead of connecting every pixels in the image, it will only connect to a small local region. For example, a 10 by 10 region in this example. And then because of this local connectivity, we require much less ways. And for example, if we have 40,000 hidden units, then we will just need 4 million parameters. That is 40,000 times 10 times 10 times basically times 100. So that's 4 million. If, as in the previous example, we have 500 hidden units, then the number of parameters we need will be 500 times 500, which is 50,000 compared to 20 million in the previous case. But 4 million parameters may be still quite a lot. Can we reduce it further? So the second idea is weight sharing. That is, we will detect the same local features across the entire image. That is, we are going to use some convolutional kernel or filter with share the same parameters across different locations. So we use the same filter to move across the whole image to generate the output to the next hidden layer. So here's more detail. So in this weight sharing scheme, each neuron on the higher layer will detect the same feature, but in different locations of the lower layer. For example, these three regions, they will use the same weights. So red, green, blue, they carry the same weights, but they will feed in different hidden units. So in this way, the output will be high if the feature is present. That is to say, the output will be activated if the feature is present. So this is kind of feature detection. So the feature will be depending on the weights in the filter. So some features may be like edge, some blob or some special shape that depend on the weights in your filter. So here is a forward pass example for a single channel image, that is gray level image. So the kernel, and which is also called filter, is gray, is yellow in this example, and it contains all the trainable weights. So basically, we have 8 trainable weights over here. The kernel size is 3 by 3. And after we do this forward pass, what we have is convoluted feature. So such convoluted feature is the output of the convolution we using our kernel with that image. So it's convoluted features. Suppose our input image is 7 by 7, and suppose our convolutional kernel is 3 by 3. So here are 2 questions. The first question is, how many units are there in the output? The second question is, how many trainable weights are there? So you may think about it, pause the video and write down your answer. And if we convolve a kernel of 3 by 3 over an image of 7 by 7, what we have is a 5 by 5 output. So there are 25 units in the output. And we will go through the details later. How many trainable weights are there? Because all the trainable weights are in the kernel, so actually we have only 9 trainable weights, which is 3 by 3 equal to 9. What about a color image? So in color image, we have 3 channels, which is red, green, and blue, which is called RGB. So color images has 3 channels of RGB. In this case, if we want to do convolution, we need a kernel which is a 3D. So it is basically a 3D tensor, more like a Rubik's Cube. In this example over here, the kernel size is 3 times 3 times 3. The first 3 in red refer to the number of channels, the number of input channels, or it is also called the number of input feature maps. And what if we want to detect many features of the input? For example, we want to detect both horizontal edges and vertical edges and maybe some other features. So what will we do to get multiple features? The answer is to have multiple convolutional filters. For example, here we have a color image of 32 by 32. So 3 is the number of color channels, and this is the image size. Then our convolution kernel will become 4D, which is 3 by 3 by 3. That is a 3D tensor, and we have 5 of them. So this will be a 4D tensor of 3 times 3 times 3 times 5. So here is an illustration. So this is one convolutional filter will produce one output, and we use 5 of them, 2, 3, 4, 5. So the first number 3 over here is the number of input channels or input feature maps, and the number 5 here is the number of output channels. So it's called output channels, or it's also called output feature maps. Right? So the 5. So here we have 5 output channels or 5 output feature maps. Another common operation is zero padding. That refers to add zeros around the border of the image. And you can add more than 1 pixel of zeros. So what do we want to add zero padding? So by doing zero padding, we can keep the next layer's width and height consistent with the previous layer. And this will also keep the information around the border of the image. Another operation is called strided convolution. So by default, we move the kernel by only 1 pixel. So in that case, the stride is 1. And we can also shift the kernel by 2. Then in this case, in this example, we shift it by 2. Then the stride, we call the stride, is 2. And you can have stride equal to 3 or more. So this is basically we shift the kernel. We may shift the kernel by more than 1 pixel when we compute the next output feature. And the objective of doing this is to try to consolidate or to summarize the information. If we use a stride of 2, then for a 7 by 7 input image, the output units will become smaller. It will become 3 by 3. So we have 9 output units. There's also another operation called transpose convolution layer. So in a conventional convolution layer, so we have an input and we use a 3, for example, 3 by 3 kernel to produce one output unit. So the output will be of a smaller size. In this case, if we have input of 5 by 5 and using 3 by 3 kernels, our output is 3 by 3. And we can so basically the dimension, right? So the dimension number of units has been reduced. And we can do transpose convolutional layer to actually increase the number of units. In this example, for example, the input is actually only the blue pixels, which is 3 by 3. And we can do a transpose convolution by also padding zeros. That is to padding zeros between every pixel and also around the corner. And then suppose we do all the paddings like this on a 3 by 3 input, we will have 7 by 7. And then we use a 3 by 3 kernel to do the convolution. Then the output is 5 by 5. You can see we go from 3 by 3 to 5 by 5. And here we go from 5 by 5 to 3 by 3. So these two are basically the inverse of each other. Right? So this is called transpose convolution layer. We will use it later in autoencoder. So these are the basic operations in convolutional neural networks. In the last session, we will look at the convolutional neural network in more detail to see how they actually produce the output.